All right, guys, yesterday we did limits of infinity. Now we're going limits of sequences, and they are so closely related. So if you got yesterday's stuff pretty good, this shouldn't be an issue for you whatsoever. Let's get it and go. All right, first of all, here's a sequence. And we did sequences, a couple weeks ago in the last chapter. That represents a sequence. Remember, you can find the first term by plugging ones in. You find the second term by plugging twos in. So what I did right here is I wrote the first several terms. If the first term is 1/2, second term is 2/3, 3/4, 4/5, 5/6, basically the numerator is one less than the denominator. So what's happening there? Well, obviously, if you look at those are getting closer and closer and closer to 1, right? I mean, 1/2, it's like 0.5, that's 0.67, 0.75, 0.8, 0.83, this is 0.875. It's getting closer and closer to being 1. It will never get there because the numerator is always 1 less, but it gets arbitrarily close. All right, so if you graph the sequence, and by the way, we didn't graph a whole lot of sequences, but when you graph them, the x-axis stands for what term number it is. The y-axis stands for what the value is. So the first term is 1/2, second term, 2/3, third term, 3/4. That's how this graph works. And if you look at the graph, it's getting also closer and closer to 1 being the horizontal asymptote, hint. So the limit of that sequence is going to be at 1. All right, so here's our definition. Definition of the limit of a sequence. A sequence with those terms has a limit L, and we write it this way. The limit approaches infinity of the sequence is L. You can also write it that way. Pretty much we go with that way all the time. If the nth term of the sequence can be made arbitrarily close to a number by taking n sufficiently large, if the limit exists, we say it converges on a number. Otherwise, if there's no limit, we say it diverges. So both of these, the pictures down here, you can see that these are graphs of sequences. This sequence is all, if you look as we go into infinity, it definitely converges on whatever L is. This one does the same thing, much like yesterday, okay, except they're sequences. All right, so this is the one we started with, and I'm going to work it much like we did the ones yesterday. I'm going to divide by the biggest degree, which is just 1. So I'm going to take each term. I'm going to shorten this a little bit. The numerator, I'm going to do n over n, dividing it by n. Denominator, I'm taking each term again. I don't know why I put 0, it should be infinity. N over n plus the limit as n approaches infinity of 1 over n. And I'm just going to work that out. So obviously on my numerator, n divided by n is 1. Denominator, I need to fix that just a little bit, sorry about that. It's just 1. My denominator, I have n divided by n again, which is 1. And here I have, still have the 1 over n. Can't divide that. Now, we know these limits though. If I have a constant, the limit is the constant, is 1. Same thing here. Limit's constant is 1. That's one we learned yesterday. If you have a denominator that is a variable and it has an integer exponent, like this one has 1, it's just 0. So my limit would be 1 over 1, which is just 1. So the limit, this limit up here, as n approaches infinity of that sequence is 1, and that's the same one we looked at a minute ago with the picture. All right, this one's a little different right here. It says determine whether the sequence is convergent or divergent. So what I'm going to do first is I'm going to list the numbers. Like if I plug 1 in there, I get -1. If I plug 2 in there, I get +1. If I plug 3 in there, I get -1. If I plug 4 in there, I get +1. 5, I think you see the pattern. This is going to go on and on and on. So the question is, does it converge on a number? Or does it never converge? Does it just stay divergent? And the answer this time is it just stays divergent. Obviously, this isn't getting close to anything. It goes just going back and forth. The graph of it looks like this. It goes -1, +1, -1, +1. Okay, so it's not converging on anything. That is what divergent looks like if you have to come up with one. All right, this is a doozy right here. You got to hang with me. This is the last slide. It says find the limit of this sequence given by that. Now, the reason this is a doozy is what I'm going to do the very first thing is that I want to write it to where I have like 1 over n, 2 over n squared, stuff like that, where I can just do a bunch of zeros, right? I want to get as many zeros as possible. So what I notice first is, sorry about that, my numerator, this has fraction multiplication in it. If you look at this 15 and n cubed, 15 is really in my numerator, n cubed is in my denominator. So what I'm going to do is I'm going to split it up a little bit. I'm going to write it Sorry about that. Like this, I'm going to take the 15 over the 6, the n over the n cubed, the n plus 1. I didn't mean n cubed there. Sorry about that. I mean n over an n, and the 2n plus 1 over an n. Now that is exactly the same thing as what we just as what is written up here. Just looks a little bit different, right? Just a math there. So I'm going to keep on breaking it down. 15 over 6 is 5 halves. N over n is 1. Now this is going to look crazy when I write this next part, but you will get this. I'm going to take this n down here and divide it into each term of my numerator. So I'm doing n divided by n. That's 1. And n, 1 divided by n is 1 over n. All right, so there's that one. This one, I'm going to do the same thing. I'm going to divide n to my numerator. It would cancel there with the 2. Just leave 2, and then leave 1 over n again. So there's all my stuff, right? So I can keep simplifying, believe it or not. 5 halves times 1 is 5 halves, times 1 plus 1 over n, times 2 over 1 over n. Now, as we learned the other day, when we first started doing limits, if I have limits of things that are terms that are multiplied together, you can break it up and do the limit of each one. So I'm going to say the limit as n approaches infinity of 5 halves times the limit as n approaches infinity of 1 plus 1 over n times the limit as n approaches infinity of 2 plus 1 over n. Okay, now the 5 halves part, piece of cake, that's a constant. It's just 5 halves. That's done. All right, the second one, remember, when you see the limit of 1 plus 1 over n, technically you could break that up and do the limit of 1 plus the limit of 1 over n. And because it's 1 over n, that's 0. 1 plus 0 is 1. Same thing here. The limit of 2 is just 2. The limit of 1 over n would be 0. 2 plus 0 is 2. So my final limit is going to be 5 halves times 1 times 2, which is 5. And that's it. Is that fun stuff or what? That is so stinking awesome. All right. We'll work on it tomorrow like we always do. Can't wait to see you. See you then.